So now we will look into the previous questions of the CSIR examination from the topic Mossbauer spectroscopy. So this is the first question. This might have mentioned in the during lecture. So the correct value of the isometric shift and its explanation for Fe2 TPP and Fe3 TPP respectively from the following are. Here TPP is the tetraphenyl porphyrinate. So they have given four statements: 0.52 mm per second, 0.45 mm per second, increase in s electron density, decrease in s electron density. This is a June 2011 question. So what we know is tetraphenyl porphyrinate will be a low spin strong field ligand, so it will form a low spin complex. So one is Fe2 and other is Fe3. So one is a D5 system and another is a D6 system. So Fe2 is a D6 system. The D6 low spin complex will have T2G6 EG0 configuration, and the D5, that is Fe3 plus low spin complex, will have T2G5 EG0 configuration. So in both the cases the electrons are absent in EG orbital. That means the EG orbitals are more towards the nucleus, so the shielding effect will be less in both the complexes. So, but there is a value difference for both the complexes because of the number of d electrons. In T2G6 there is 6 d electrons and T2G5 there is 5 d electrons. So more number of d electrons, more will be the shielding effect. So the more shielding by the d electrons to the s electrons, so the s electron density will be less. Shielding is higher, the electron density will be less, isomer shift will be high. So for T2G6 there is 6 d electrons and T2G5 there is 5 d electrons. So due to the presence of one extra electron in T2G complex, so or the T2G6 system, that is Fe2 system, it will have more d electrons and more shielding, so less s electron density and higher isomer shift value. So Fe2 plus will have a higher value of 0.52 than the Fe3 plus, the value is 0.45. So Fe2A and Fe3B. Then in both the system the EG electrons are absent. So the EG electrons are absent, that leads to the less shielding towards the nucleus. So the less shielding towards the s electron. So the s electron density will be high in both the complexes because of the absence of the electrons in the EG orbital. So that there is an increase in s electron density in both the cases. So A and increase in s electron density and B also increase in s electron density. So AC, BC, option B is the right answer for this question. So this is the right answer for the question. D6 is more shielded, lesser s electron density compared to Fe3 plus and greater isomer shift value. So Fe3 plus D5 shielding is less compared to Fe2 plus, greater s electron density and lesser isomer shift. Okay, so option B is the right answer. And the next question is, consider the compounds SNF4, SNCl4, R3SNCl. The quadrupole splitting are observed for. So the reason or the reason for the quadrupole splitting is due to the symmetry loss, or there is an asymmetry, or they either the electron asymmetry in the distribution, or the asymmetry in the ligand asymmetry. So here SNF4 is a special, you have to know the structure of these compounds. SNF4 is forming a polymeric structure, while SNCl4 is tetrahedral and R3SNCl is also tetrahedral. But due to the difference in substitution, R3SNCl is not having any kind of symmetry, even though it is a tetrahedral structure. But in SNCl4, all the substitutions are same. It is forming tetrahedral symmetry. So there is an asymmetry in this compound. So there is no quadrupole splitting for SNCl4. While in SNF4 is a polymeric structure. So again there is no there is asymmetry in the compound. So that is also forming a quadrupole splitting. So both the compounds SNF4 and R3SNCl showing the quadrupole splitting. So option D, A and C is the right answer. This is a June 2011 question. The next question is, in Mossbauer experiment, the source 14.4 kilo electron volt is moved towards the observer at a velocity of 2.2 millimeter per second. The shifting frequency of the source for the sample is, this is a December 2011 question, and there I have given the four options, and it is given in megahertz. So you have to know the equation for the shifting frequency. We can calculate the shifting frequency by the equation. Shifting frequency is equal to nu into V by C. So nu is given, the nu is given as 3.48 into 10 raised to 12 megahertz, and what they have given is, the velocity is given 2.2 millimeter per second. So shifting frequency is equal to nu into E by C. C you already know, 3 into 10 raised to 8. So since it is in mega electron volt, we have to convert this into mega electron volt from the since the options are given in megahertz, we have to convert the value in hertz. So that is why we took the value in hertz, 3.48 into 10 raised to 12. So if you can substitute the values, you will get the value of 25.5 megahertz. The option B is the right answer for this question. So the next question is, the recoil energy of the Mossbauer nuclei of mass 139 AMU is 2.5 mega electron volt. The energy emitted by the nucleus in kilo electron volt is, so they have given four options: 20, 12.5, 15, 20.5 and 25. So this is a December 2012 question. So you know the recoil energy equation. E recoil energy is ER is equal to E gamma square divided by 2 mc square. So here E gamma is the energy emitted by the nucleus. So that is the gamma radiation. So during the gamma radiation, the amount of energy emitted is E gamma, and this can also written in another form, ER is equal to 536 E gamma square divided by M. So this is the equation in electron volt, and here the mass is presented in AMU. If the mass is in AMU and the E recoil is in electron volt, then this is the equation. So what they have given is the mass in AMU, 139 AMU, and the recoil energy is given in electron volt. So you have to substitute in this equation E gamma, ER is equal to 536 E gamma square divided by M. So here you have to convert the AMU into the electron volt. So 1 AMU is equal to 931.5 electron volt MeV. So you can convert this value by substituting this in this equation. So 2.5 is equal to 536 E gamma square divided by 139 into, here 139 AMU, so 139 into 931.5 MeV. So E gamma is equal to, if you will get the E gamma square value, if you take the root of this value, you will get 25 kilo electron volt. So that is the option. And the next question is, among the following, those can act as a Mossbauer nuclei are. So one is iodine 129, cobalt 57, iron 57 and Sb 121. So here iodine, here cobalt 57 can act as a source. It is not the nuclei. So you have to read the question thoroughly. What they have given is the following, which one of the following can act as a Mossbauer nuclei. It is not about the source. So here the cobalt 57 is source. All other compounds can, or all other nucleus can act as a Mossbauer nuclei. So we can evaluate using the Mossbauer spectroscopy all other nucleus, iodine 129, iron 57 and Sb 121. So 1, 3 and 4, other than the cobalt 57, all can act as a Mossbauer nuclei. So 1, 3 and 4, option D is the right answer for this question. And the next question is, the correct order of isomeric shift in Mossbauer spectra of iron compounds. This is a December 2014 question. So Fe2, Fe3 and Fe4 systems are given. So Fe2 is having a D6 electrons and D3, D5 electrons and Fe4, D4 electrons. So the number of D electrons are decreasing upon increase in the oxidation state. So if the number of D electrons are more will be the shielding by the D electrons to the S electrons. So if the shielding is high, S electron density will be low and isomer shift will be high. So higher the D electrons, lower the S electron density, higher will be the isomer shift. Lower the number of D electrons, higher will be the S electron density, lower will be the isomer shift. So lower the D electrons. So Fe4 system is having a D4 electron, that is 4 electrons, and Fe2 is having a 6 electrons. Higher the D electrons, higher will be the shielding, lower will be the S electron density, higher will be the isomer shift. So Fe2 is having a higher D electrons and hence higher isomer shift value. Fe4 is having lower D electrons, so lower the isomer shift value. So option 1 is the right answer. Fe2 greater than Fe3 greater than Fe4. So oxidation state increases, isomer shift decreases. Option A is the right answer. So the next question is, Mossbauer spectrum of a metal complex gives information about oxidation state and spin state of the metal, types of ligands coordinated to the metal, nuclear spin state of the metal, geometry of the metal. So Mossbauer spectrum of a metal complex give information about. If you know the Mossbauer spectrum of a compound, you can easily identify the oxidation state, spin state of the metal, and also the types of ligand coordinated to the metal. If there is an asymmetry, then there will be definitely a coropole splitting. So if you will get the geometry of the compound, and if there is a ambidentate ligand or such kind of ligand, there will be some shifting in the Mossbauer spectra upon increasing the temperature or decreasing the temperature. So you will get definitely you will get the information about the type of ligands coordinate to the metal, oxidation state of the metal, and the spin state of the metal. If it changes the spin, then definitely there is a change in the spectra. So 1, 2 and 4 is the option. So option C is the right answer. Mossbauer spectra gives information about the oxidation state, low spin or high spin state, and also give the ligand and ligand types of ligands and the geometry of the metal. And the next question is, to record the Mossbauer spectrum of iron containing sample, a source X is used. X after a nuclear transformation gives gamma radiation used in the Mossbauer spectroscopy. X, Y respectively are. So what we are getting, iron containing sample, a source X is used. What is the source used in, to determine the iron containing sample? That is the cobalt 57. Then X after nuclear transformation forms Y, gives gamma radiation. So X after a nuclear transformation form Y and gives gamma radiation used in the Mossbauer spectroscopy. So cobalt 57 upon electron capture forming a Y and also gives the gamma radiation used in the Mossbauer spectroscopy. So cobalt 57 and electron capture is the, so X after a nuclear transformation. What is a nuclear transformation happening? That is the electron capture. So electron capture and cobalt 57 is the answer. So option 3 is the right answer. This is a June 2016 question. Option C 3 is the right answer. The next question is, the Mossbauer spectrum of the complex Fe110 phenanthroline NCS twice shows 2 lines at 300 Kelvin, 4 lines at 186 Kelvin and 2 lines at 77 Kelvin. This can be attributed to the change in the coordination mode of the NCS, change in the spin state of the ion, cis-trans isomerism, and change in the metal ligand bond distance. So you know 110 phenanthroline NCS complex. Here NCS is a ligand. So NCS is an ambidentate ligand. Whether it can coordinate to the coordinated through the nitrogen or through the sulfur. So the coordination site of this NCS may change. So this change in the coordination site will give the will give the different lines in the Mossbauer spectroscopy. And also, if it is binding through the NCS and if it is binding through the SCN, there will be the change in the field strength of the ligand. So SCN is a weak field ligand and also NCS is a strong field ligand. So there will be a change in the spin. So the spin state also will be changing. So this is the reason for getting different lines at a different temperature. So the change in the coordination mode of NCS and also the change in the spin state of the ion, A and B are the option for this change in the number of lines. So option A is the right answer. So these are all about the questions from the Mossbauer spectroscopy. Thank you all.